In 1937, the Atlantic crossing of the airship Hindenburg ended in disaster. While docking in Lakehurst, New Jersey, the 200,000 cubic meters of hydrogen gas explosively caught on fire. While officially unconfirmed to this day, the cause was a well-known physical phenomenon, the spontaneous discharge of static electricity. This phenomenon comes about quite simply. If two initially neutral objects come into contact, there is a charge transfer, which then remains after they are separated, distributing itself over the entire surface. On contact with other conductive objects or grounding, the charge suddenly escapes and can possibly arc over shortly before contact. In the Hindenburg case, a spark presumably ignited the highly explosive gas. Back to the present. In the age of microelectronics, failures and interference caused by static discharge have gained dramatically in significance. Because of their constantly decreasing geometry coupled with the increase in their integration density, microelectronic components have become more and more sensitive to this discharge. The official designation for this phenomenon is ESD, electrostatic discharge. It's the term we'll be using from now on.
Because we believe that primarily highly integrated ICs are endangered, we often overlook the fact that simple components like optoelectronic devices or diodes or even power semiconductors can be destroyed by ESD.
Before we began implementing ESD protective measures, we had plenty of failures. This is an unacceptable situation when cost-intensive components are being used.
Reliable ESD protection is only possible when everybody involved knows where its causes and effects are located. In production practice, this means protective measures from wafer production all the way to back-end and component testing, from development and assembly to the delivery of the finished piece of equipment. Charges are generated and circulate everywhere. We all know this famous crackling sound when we take off a sweater. A few examples should sensitize us to the number of charges that might come about every day. By the way, we can only feel discharges from voltages of about 3,000. Sometimes we don't even notice when a charge is generated. Or inappropriate materials like these non-conductive shipping tubes are used. Even the electrostatic field of an unreleased monitor can lead to uncontrolled ESD stresses. To clarify this point, one final example. When we touch an electrical circuit with our bare fingers, the result has the same energy density as a lightning bolt slamming into a tree. The damage to a component is quite similar. Charred connections, burned and broken surfaces, and even the remnants of explosions. This is why Siemens developed HLSEP, a complete strategy for external ESD protection based on international standards. The objective is to avoid ESD failures, from wafer production all the way to delivery to the customer. The most important factor here is our awareness, our heightened sensitivity to ESD events, followed by so-called internal protection. This is ESD hardening of the components through design procedures and specific ESD tests, as well as external protection to reduce ESD stresses organized by HLSEP. The basic prerogative involves handling the components in a specially equipped ESD protective area, EPA for short. This is clearly identified and may only be entered by properly equipped and trained personnel. The EPA is based on the fundamental principle of only allowing charges to dissipate under controlled circumstances to avoid potential differences. As early as the planning and construction stage, we have to see to it that the floor is grounded and made of dissipative material. The shelves and work surfaces have defined ground resistance ranges to make sure charges will not dissipate either too quickly or too slowly. Movable storage equipment is also fitted with groundable wheels. The same principle applies to chair wheels. The covers and upholstery are also made of dissipative materials. The use of highly chargeable insulated materials, especially in clean rooms, is often unavoidable for process reasons. They can be neutralized not by grounding, but rather only through the use of an ionizer. One highly sensitive area, for instance, is mask technology.
Throughout the production of semiconductors, there are any number of procedures which might result in ESD damage, such as testing ICs while still in the wafer stage, bonding the connecting wires, trim and form, or checking the component with attachable electrodes.
Now let's turn to the main problem, the people who work here. EPAs may only be entered with dissipative released ESD footwear. It is also important to keep the coat constantly fastened. Static charges also have a helpful side effect. They can be locked in or shielded. If the coat is unfastened, the electrostatic field of someone's personal clothing might exert a direct influence on the component. In special cases, instructions may be given to wear dissipative finger cots or gloves. The most important item here, however, is the wrist strap, which should always be tested before entering the labeled EPA. As should the ground resistance of the footwear. A heel strap like this one is available for visitors.
Of course, we sometimes have problems observing these regulations, but daily routine causes even the most reliable individuals to forget the occasional test procedure.
To prevent carelessness from gaining the upper hand, especially in large plants, the gate only opens after the tests have all been passed. When handling components, even in laboratories, some fundamental rules should be strictly observed. For example, outer packing should be torn open outside the EPA until the ESD label is visible. Connect the wrist strap, then cut open the adhesive sealing material. Do not tear it open. Only approved and properly labeled packing and filling material may be used in the EPA. In other words, no highly conductive materials like styrofoam. Components being unpacked should only come into contact with dissipative materials to avoid hard discharges. If you think this will eliminate every hazard, you're wrong. Remember friction, which, as this experiment demonstrates, can come about at any time during a fully automated manufacturing process. This is why only suitable packing should be used here as well. In production, we have to use defined dissipation, ionizers, and the proper selection of material to keep ESD under control right down the line. Even so, a component charged by unpacking or sliding along the material track might discharge on contact with a metal machine part. This is why modern assembly equipment uses the pick-and-place principle, virtually without sliding. The skyrocketing development of manufacturing technologies calls for ongoing research and testing, because practicable solutions can only be found in a balance of potentials inside an EPA. This is why the Siemens Semiconductor's ESD laboratory is optimizing the resistance of work surfaces, tools, machinery, and packing materials. The widest variety of materials and shapes is subjected to ongoing testing. Precise results call for high precision and the devotion of a great deal of time to the measuring process. Several environmental factors such as humidity or the selection of test methods also have an effect on results. Incidentally, should components need to be shipped for failure analysis, they should of course also be provided with ESD protective packing, so that no damage caused en route can obscure the actual failure to be tested. This is the only way a precise failure analysis will be possible. Thoroughgoing ESD protection can only be practiced with the active participation of everyone involved. Daily routine often harbors a great hazard. This is why ESD awareness and a full knowledge of physical causes and their effects are so crucial. Moreover, every ESD staff member is responsible for testing his grounding aids, such as wrist straps and footwear. In addition to the HLESD coordinator and the local ESD representative, Siemens also has an abundance of proven procedures and technical periphery at its beck and call to prevent ESD damage. Customers and other companies are also able to take advantage of this know-how and technical support. All Siemens staff members can access an ESD online training program on the intranet, where the latest test results from the ESD laboratory are also made available worldwide.
Our latest figures prove that failures rapidly decreased after Siemens ESD training and the thoroughgoing implementation of ESD protective measures.
The minimization of dimensions in microelectronics is steadily on the move. This means ESD sensitivity will keep rising, despite protective measures inside the devices. This is why the future development of ESD protective measures at Siemens will always be one step ahead of progress in production technology.